Thanks, Alex, for starting the recording. And we'll get started. So thanks for coming out here at the Intermediate Databases and SQL workshop. My name is Casey McLaughlin, and I'll be standing in front of you guys for 90 minutes or so. If you aren't familiar with the Research Computing Center, we are located on the ground floor of this building, and that kind of got us squirreled away in the basement. I've been working with databases for over 20 years now, so I feel somewhat qualified to just be dangerous enough to instruct you guys on it. Did anybody attend the Intro to SQL workshop back in October? Show of hands. Anybody online attend? And you can just put a thumbs up in the chat if you did. Okay, well, this workshop was originally meant to build on that workshop, but I'm going to spend a little bit more time going over the recap of the Intro to SQL workshop, since I guess you all are new to SQL. Who has SQL experience? Cool, well, that's great. All right, so we'll play it by ear then. All right, let's see. That's this not. All right. So this is the first time that this I am teaching this workshop. So this curriculum is brand new. So I am not sure how much of this we're going to be able to get through today. You guys are the guinea pigs. Again, I said that at the intro workshop back in October. But I want to quickly review the stuff we went over in October just to set the context. And then I will get into many-to-many relationships. We're going to discuss normal forms. And then a little side jump into entity relation diagrams. And then we're going to write as much SQL as time allows. So let's just jump right in. What we covered in the first shot workshop. So this is a list of the things that we went over in the first workshop, and I'll leave it on the screen here for a minute or two. You guys can look at it. All right. So we discussed what a relational database is, and I like the second definition on this slide better. It really describes what a relational database is supposed to do better than the official Wikipedia one. The MySQL page has a slightly better definition, but concepts like these are best explained through an example, which we did. So, and then I explain what SQL is, structured query language, and it's the primary query mechanism for relational databases. All right, and then we talked about tooling, software. So SQL or relational databases is a protocol or a concept, and it needs software to implement that, just like any other protocol. So there are many commercial offerings and open source offerings. It is a client server system most of the time. There are some exceptions like SQLite and Microsoft Access actually comes bundled with Office, and it provides both the backend and the user interface in one piece of software. But most of the time, your server is running on a system and you use a client to connect remotely to that system. So we chose in October MySQL, and as a client, IDSQL. And I'll continue to use those for this presentation today. All right, and then we built a relational database. So we started off our talk in October by dreaming up a use case for a relational database. And we ended up having a restaurant, and the restaurant had one requirement to start with. It needed to track customers' names, email addresses, birthdays, and favorite dishes. And so we identified some nouns in that sentence. So always look for a noun when you're modeling the database. And so we focused on the customers and dishes to start with. And sorry, jumping ahead here. So we started off by building a spreadsheet for each of our customers and our dishes. And we added the fields, first name, last name, email address, birthday, favorite dish. And then we created another worksheet for dishes. And so pizza, chicken, and fish. Keep it simple, only 3 items. And then we created our keys. So in a spreadsheet, I mentioned in October that the spreadsheet software always keeps track of the row identifiers for you via this sidebar here. But in a relational database, you need to set that up yourself. And each record has what's called a primary key. So I like to stick with ID for the column name for the primary key. So ID, we added our ID column here, and it's added just 1, 2, 3, 4, 5, 6, 7, 8 incrementing integers. And as you see here, I've done it for dishes too. All right. All right. And then we got into some terminology differences between spreadsheets and relational databases. So a workbook and a spreadsheet is the entirety of the worksheet. So think about these worksheets being all the way over to here on the screen. But in databases, it's called a schema. A worksheet, each individual worksheet is called a table. So I'll refer to these as tables from here on out. And rows in the spreadsheet are referred to as records or tuples in the database. I'm going to use the term record because nobody uses tuple, as far as I know. And then finally, columns in the spreadsheet are called field attributes or fields. I'm going to use the field terminology in this presentation like I did in October. All right. All right. And then we talked about the need for IDs to be synthetic keys. And what I meant by surrogate or synthetic keys, those two terms are synonymous in database context, is that they have nothing to do with any of the data in the row that it's representing, and the record, rather, it's representing. So we're going to focus on record 2 here. 2 has nothing to do with Lee King or his birthday or his favorite dish or anything. It's just an arbitrary value that we've assigned to that record. Likewise, 1 has nothing to do with pizza, but it's an arbitrary value that we've assigned to that record. Now, the dish price certainly has to do with the pizza because the pizza costs $6. And likewise, there it is. Lee King's birthday has to do with him because that's the day he was born on. Furthermore, his favorite dish is chicken. So, you know, that has to do with Lee King too, right? His favorite dish is chicken. But number 2 is a synthetic key because it has absolutely nothing to do with the person that it's representing in the database. And that's an important concept because synthetic keys should always be used for primary identifiers. All right. Then we talked about some terminology. So again, reviewing fields, records, primary key, and table. All right, so every database has a primary, table has a primary key. And again, it should be a surrogate or a synthetic key. How much time am I? Okay, 15 minutes, okay. All right, then we talked about relationships between tables. And so this table contains all the dishes, and this table contains all the customers. And our favorite dish is a foreign key relationship to the primary key in the dishes table. And that should be intuitive to you at this level of simplicity, but for example, elevator's favorite dish is chicken, because chicken has an ID of 2 and it references the number 2 in the dishes table. With me so far? Cool. All right. So we modeled all of this in an actual relational database. And I'm using Heidi SQL as my client. And you can see that if I flip over to the data tab, I've got all of my customers in there and my dishes. And I have named my columns or fields consistently. First underscore name, last underscore name, email, birth date, favorite underscore dish underscore ID. And then also so I want to point out here that everything is important in database design, and especially naming conventions. So pick a system and stick to it. For foreign keys, like favorite dish ID, I'm using the table name and the column or the field name, which is usually the primary key, as the suffix for whatever I use for the name. So favorite underscore dish underscore ID. And we'll see that in more detail in a minute. Okay. We also went over basic data types. So in October, and they're pretty much similar to any given programming language. So if you're familiar with any programming languages, you're going to be familiar with data types. But they're they're different depending on which RDMS software you use. So these are some of the more common ones though. And SQL is a standard that defines what necessary data types there are. So the first 3 are like string types, the second 3 are number types, and then we have date time. And there's a few more like booleans and tiny ints and stuff like that. But I think that's it. All right. So then we moved on to talk about expanding our business use case. So we added another requirement. XYZ restaurant also hosts events and would like to keep track of it, names, dates, times, and contacts for events. So again, we tried to suss out the table from the nouns in the sentence, and we determined it was events. And so we created an events table. And likewise, with keeping consistent naming conventions, we have ID columns on all the table name or tables in our database. We have a name and a date and an organizer. And I'll see here that the organizer is a foreign key, and it refers to the ID of the customer in the customers table. So then we discussed one-to-many relationships, which is the first type of relationship in MySQL or SQL, or relational databases, I should say. So there is one customer that can organize many events. Likewise, there is one dish that can have many customers be the favorite of, right? Many customers be the favorite of. Multiple customers can select their favorite dish from this table, right? So this is a one-to-many relationship. Dishes is on the one side and customers is on the many side. And it's inverse for the events. Customers is on the one side of this relationship and events is on the many side. All this is defined as a schema. And then this representation of it is called an entity relationship diagram. So I then showed an actual entity relation diagram from out in the wild. This is just a random image from somebody's database, but it shows like what entity relationships actually look like out in the wild. And we're going to talk about these in further details today. All right, then we actually got down to business writing SQL. And so I'm going to flip over to my database now. So we've got a couple other tables here, which I preloaded for today's talk. Dishes and orders and dishes and orders. We're going to talk about those in a little while, but I just want you to focus for now on the customers, dishes, and events tables. So in my database client, I've got this query builder, which you can enter SQL into. So we're going to enter in some queries from October. Select star from people. Oh, customers, sorry. And the basic syntax for SQL queries is keyword, fields or columns, keyword, table name, constraints or conditions or predicates. You can use all those three terms interchangeably or synonymously. So our basic query just says, give me everything from the customers table, and that's represented by an asterisk. Now we can add a condition to it, also called a predicate. Last name equals big. And we only get one record, of course. Or we can sort by a column name. Sorry, forgetting my something stuff I've been doing for years now. Must be nervous. Okay. So, any questions about basic SQL? Some other examples. We'll get into joins in a second here. Robin Banks or Shay King don't have favorite dishes, but everybody else does, right? So, and so notice how it's automatically ordering by favorite dish ID. Anyhow, we will do some more complex queries today. All right, I want to talk about joins now, which we discussed also in October. So there are two types of joins, more types of joins than that, but we discussed two types of joins in October. One is an outer join, and it's used, the keyword for that is left join. And that's when you want to see all records in this table, customers table. It's regardless of now whether or not they have a relationship with this table. So we'll see that now. Just get my notes clause. So I'm going to put the from clause on a new line. And then left join dishes on customers favorite dish ID equals dishes ID. All right. Now we're going to review some syntax here. We're getting the first and last names and the name of the dish from these two tables. From customers, that's obvious, self-explanatory, I hope. Left join dishes. On, this is the foreign key field in the customers table that refers to the primary key in the dishes table. And I've written it out I've written out the table names instead of the aliases, and I'll get into aliases in a little bit in this query. So customers, dishes on favorite dish ID equals primary key. And what happens is I get a list of everything. All right. Now we're gonna narrow it down to some fields. So first name, last name, name. All right. Now that name column is ambiguous, right? It is not clearly the dish name. So I can add an alias to it with the as keyword. And that makes it clear in my output what this column is, or this field is. Now, since we're doing a left join, you notice that some records in here are null. So they don't have a favorite dish. So if I wanted to do an inner join, which is the other kind of join, it would only select records in the customers table that also have corresponding relationships to the dishes table. So this query, this left join query here, just returned 25 rows. If I execute this inner join query, you can see that two customers don't have favorite dishes. And notice that it automatically orders by dishes, even though I don't have that clause in my query. Now, if I wanted to explicitly order by another field, I can say order by last name, and it would know, based on the fact that I instructed it to do so, that I need to order by last name. All right. This is just a slide for the inner join. And we left off actually we did not leave off, but we covered also aggregate functions. And these are going to be different depending on which database server you're using, so or RDMS system you're using. There are some common ones, though, defined by the SQL specification, like count, sum, AVG, min, max. But let's see. So select count ID. So this is a convenient way to get a count of everybody, all of our customers, right? Also, we can look at the total price of our menu items. Select sum price from dishes using the sum button. So the total price of all our items on the menu are $22.50. I'll do one more aggregate query, so this is a MySQL specific function, I think. The semantic is different if you're using a different RDMS. But you can see that I just combined this output into a single column using the concat function. And if I want to make it extra snazzy, I can add an alias to the report. All of our customers, right? All right. And finally, we ended up talking about modification SQL queries. So I'm not going to demonstrate these today for lack of time, but we covered adding records to tables, updating records in tables, and basically, if you want to run the update SQL query, you better best have a where clause in it. Otherwise, it will update all the rows in the table. And finally, delete. Likewise, if you just say delete from customers, the database engine will wipe out your entire customers' records. So you better have a where clause in that. And that took up 90 minutes. So I had to let everybody go after that. But we've only taken up a third of the time. So we'll get on with the new material. But I want to pause here and see if anybody has any questions before we continue. Any questions online? All right. Well, let's get into some new material then. Moving on. And I'm going to reset my timer here. All right. We're only 5 minutes behind, so that's good. All right. So let's add another business requirement to our list of requirements. We also now want to track orders, and the orders can have multiple dishes. All right, so we need a new table, right? Orders, which I think is fairly obvious. So let's see if we can brainstorm some fields that we might need in the order table. Well, we're going to have the ID field, so we need a primary key. And it should be arbitrary and not have anything to do with the rest of the records. So I always put the ID first. And then we're going to need to know who placed the order, right? We need to know who to deliver it to. So we're going to have a customer ID foreign key field in that orders table. And then we want to know when it's ordered, so we can prioritize. And then finally, we need to know what dishes were ordered. Now remember, there can be many dishes in one order. So how do we model that? Anybody have any ideas? All right. I guess I'm here to teach you about databases, so it's my job to say. Yes.
I was gonna say, I think before you just had like the ID number for the type of dish, but now you'd have to find a way to create combinations of different dishes, I guess.
That's right, because there can be many dishes. So he said before we just had the ID number of the dish. And I think you're talking about this favorite dish ID, right?
Yes, yes.
But that's just the customer's favorite dish. That's a nice to know, right? If they're placing an order, we have to know what is in that order, right? So we need a way to store multiple values. So we can do this. Dish 1, dish 2, dish 3, create a new column or field for every dish they order, but this has obvious drawbacks, right? First of all, they are limited to 3 or less dishes per order, and that doesn't seem like a good way to run a business. Yes.
Just to answer to your question from online, you could insert a dish number field into the in text mode.
Oh, great. Yes. So the online user, in case anybody didn't hear it, said that we can enter a single column, right? Single field that includes all the dish IDs. Well, we know this is out, obviously, because this doesn't handle people that order 4 or more dishes. Online, I think the person was talking about adding a single field that includes a comma separated list or something like that, right? However, what if we delete a dish from the order? Like the customer decides he wanted fish and just changed his mind. Then we would have to go edit the text, right? Or I don't know, this just seems like a non-ideal way of managing this data. And it's also a violation of first normal form, which states that every cell should have 1 atomic value of any one. So this is out too. Sorry, online user. So what should we do? Well, okay, so let's back up. Take a clear look at this. Orders can have multiple dishes. We call that in SQL parlance many dishes. 1 or more is defined by the term many. But conversely, dishes can be part of many orders, right? We only have a finite number of dishes, which is for now 3. And well, those are gonna be placed into multiple orders, right? Like two people can order pizza. So again, this is what we refer to as a many-to-many relationship. Let me get caught up here. Okay. So many-to-many relationships not exist in relational databases. There's no such thing as a many-to-many relationship. There are just one-to-many relationships. So foreign keys and primary keys are referenced. So we will need to add a third table, which is called a join table, to this. Let's see one. So first, we'll have the orders over here and the dishes. And we know that many orders can be related to many dishes. So we'll create a new table, our join table, and call it orders dishes, at least to start with. And we'll create some relationships. One to many, one to many. All right. So let me explain how this is going to work. We'll have a single order, which can contain many dishes. So we'll insert a record for every dish and order combination into this join table here. So this is demonstrated on the next slide. Oops. All right. So we'll have a foreign key that refers back to the orders table, and another foreign key for each record that refers back to the dishes table. And we'll have order number 1. See that? All right, and then there's 2 dishes in order number 1. So this order contains both fish and pizza, but it's the same order. Now, I like this approach because each relationship is what's the word I'm looking for? Represented by a single row that can be added or removed in the database. So another reminder, there are no such thing as many-to-many relationships in relational databases. Only one-to-many relationships with join tables. Now, that doesn't stop us from having some shorthand to eliminate the join table that we know is there already. So this is how it's often represented in ER diagrams, entity relationship diagrams, is N:(N). I don't like the shorthand. I usually like to show the join tables in the entity relationship diagrams, but we'll get into those in just a minute. But you'll notice that it's N has a Nancy instead of M as in mother. And that has to do with the academic background of this relational database theory. N is supposed to mean any number, so 0 to infinity. It represents a number. All right. All right, and then we have another relationship off our orders table that is a standard many to one. So a customer, we hope, will place many orders with our restaurant. So the customer side is the one side, it's the side that has the primary key, and then the orders table has the foreign key to the customer's table. All right. Does that all make sense? Any questions? All right, just holler if there's a question. I want to stop and talk about normalization for a few minutes. I'll reset the timer here. Track. All right. So first, the definition. The systematic process of organizing data in a relational database to reduce data redundancy and improve data integrity. what does that even mean? Also, furthermore, it involves decomposing tables into smaller, well-structured tables, and finding relationships between them according to specific rules. Okay, it's basically comes down to, these are the rules you need to follow to create a good relational database model. So we're going to talk about first, second, and third normal forms today. And that's mostly what you'll need to know going forward in perpetuity. There are more normal forms, but most databases are considered good enough, a good enough balance between understandability and correctability, I guess, say it. It's a trade-off. So third normal form is usually where database modeling stops. All right. Okay, so first normal form rules. Values in each cell should be atomic. So that means each cell in your database should contain one and only one value. We covered that a minute ago when we were discussing how to model the dishes table for value in the orders table. And row order should not matter. So what that means is these is another way of saying these primary keys should be arbitrary values, because you're going to delete and add orders or customers or whatever data willy-nilly, and it should not matter what order the keys go in. So one way of let's review our orders and dishes schema model that we created just a moment ago. So again, dishes is a one-to-many relationship with the orders dishes join table, and orders is a one-to-many relationship with dishes join table. And notice that I'm using entity relationship nomenclature in here, so one-to-many. You'll notice something I added to the join table, though, is an ID primary key to it. So originally we just had the two foreign keys, our orders dishes table, but I've added a primary key, and that is making it first normal form compliant. It also makes it easier to reason about the data, because I can say now that the fish order in order number 1 has an ID of 2. So presumably, let's say our customer accidentally ordered 2 fish orders, which are represented by ID rows 1 and 2 in the join table now, wants to accidentally click the order dish twice and wants to remove the second order. Well, now the software knows that it should just eliminate row 2 in the orders dishes table. Easy peasy. While we're at it, and this is not anything to do with first normal form, but it is good. It has to do with good database design. I like to name my join tables more descriptive. So instead of orders dishes, which just defines or states the two tables that the join table is connecting the relationship, I like to name them dishes and orders. I think that's a better way of naming our join tables. It's important. Naming is important in computer science, right? All right. Also, remember this proposed solution is also a violation of first normal form because it has multiple values in a single column. So, or a single field cell. So this is the proper solution instead of this. All right. And then we're going to talk about code smells here. Like code smells means something, a potential problem, a pitfall in your logic. Look out for columns with multiple values, obviously, and join tables without clear IDs. So without this primary identifier, the join table is not first normal form compliant. All right, that's first normal form. Let's move on to second normal form. No value in a table should depend on any or only part of a key that can be used to uniquely identify a row. What does that even mean? I feel like the second normal form definition is kind of word soup. So I'm going to use an example to present a first or a second normal form violation and then its solution. So we'll look at the events table that we created in October for this example. So the name, date, time, customer's ID. What if we have a restaurant with multiple event locations available? So something like this. We'll add a location column to each event. Now, the organizer is a foreign key back to the customer's table. Now, this has nothing to do with second normal form, but it does have to do with good naming conventions because that is not immediately clear that that is a relationship field. You know, it has numbers as the identifiers. So we know it's a foreign key, but we don't know what's a foreign key to. So I like to name my field names consistently customer ID. So that tells us what table it's a foreign key to and what field it's referencing. Just food for thought. All right, back to second normal form. So we have a main dining room level 1, main dining room level 2, terrace. Those are our 3 locations from the data here. So what if we want to change the name of the dining room? What could we do? So main dining room level 1 becomes like the Alfred P. Sloan dining room or something. We could run an update query, update all the records for main dining room level 1. That's one solution. A better way to do it would be to, well, let's talk about that in a second. Also, what do we want to add additional information about each location, such as price? We book that location. So we would have to add another column out here to the right, location underscore price or something like that. Now we have, when we want to change the price of the location, we have to update all the records in the events table that have that location identified. So that should be your first warning bell / code smell that something needs to be changed about the schema. Okay. The solution is to make each location its own, well, add a new table and make each location its own record. So then we'll replace the location column in the events table with a foreign key that references the primary key on the locations. So we can add as much information about each location as we need to. And that is an example of a second normal form violation and a solution. So what to be on the lookout for as you're designing your schema is lots of repeating data in tables. If you have a lot of repeating fields data, then you probably ought to think about, does this warrant a separate table? All right, finally, we're going to talk about third normal form. And it states values should not be stored if they can be calculated from another non-key field. Again, what's that even mean? So we're going to demonstrate with a 4th business use case. XYZ restaurant offers a senior discount of up 50% off normal menu prices. Now, there's a lot missing in this business use case. First of all, what constitutes a senior? You know, like 55, 65, who knows? But we'll just assume, we're just gonna ignore all that for now and just focus on the 50% off part. So we could add another column to our dishes table with this, a new senior price column, right, or field, rather. Using spreadsheet terminology when explaining relational databases. Shame on me. However, what if inflation happens and we need to raise the price of pizza to $13 instead of 10? Now we have to update 2 columns in the database. And that is a third normal form no-no. That's what calculated from another non-key field means. It means senior prices such as discounts such as senior prices, rather, are no good to store. So where should we calculate that? Well, that actually belongs in your query, which if we have time, I will show you how to do that today. Or you're even better, assuming that an application of some sort for the user interface, it should be in the business logic of your code. All right. Those are the 3 normal forms. And to keep this presentation consistent, I just added this food smell slide for this too. Out for the same. All right. And then there's more normal forms. Like I said, there's technically 3 more, along with some edge case normal forms. But again, I think that this, if you get to third normal form, it's generally good enough. All right. So any questions about normal forms? Yes.
So those are like standards, right? Like when you're looking at the data. Okay.
Yes.
And also, if you were like to concatenate like your first name with the last name like you did before, would that still be atomic or would it not?
Ooh, that's a good question. So the question for our online viewers, in case you didn't hear it, was these are standards that are industry-wide. So if you look up normal form databases on the internet, you get these rules. Second question was if you put the first name and last name columns together in a database, would that be a violation of first normal form? So she's talking about combining the first name and last name columns into one. Well, that really depends on your business. You don't need to track first names and last names separately, then sure, put them together. That really depends on your business use case. However, I would err on the side of atomicity. You never know when you have to sort by people's last names, right? So if you have those stored together, you're going to have a hard time doing that. You can sort by people's first names, but not their last names easily. So there's always a good reason to break down data into its most discrete pieces when you're designing a database. And sometimes you make a mistake and you have to go back and modify your design even though there's already data in it to break out fields that you thought could be put together into separate ones. All right, good questions. Any others? All right, well, let's take a second to look at our comprehensive data schema here before we move on to querying it. So these are our tables. Now we noticed that we don't have the event locations table from the second normal form discussion. We'll just go back to pretending our restaurant is small and only has 1 dining area that can be booked in its entirety. But this is our schema that describes all of the tables and the relationships. And it's getting quite messy. It's hard to follow. So let's take a few moments and look at some ER diagram standards. So the first one is generated by a tool called Beta Grip, which I've used to help put this presentation together. And I really don't like it very much. So you'll notice though that the arrows point from the many side of the relationship to the one side. So there can be one dish that is the favorite dish of many customers. Likewise, each order is associated with a single customer. But it really doesn't tell you which foreign key fields map to which primary key fields clearly. In addition to that, it really, I mean, this notation syntax, I really don't like. It's messy and it kind of covers some of the other information. So let's look at another one that's slightly better. This was generated by a tool called MySQL Workbench. It's free. So I thought I'd decide to try it out. And it generated this diagram, entity relationship diagram of our database. And this is a little bit better. It still doesn't show which particular foreign key fields map to the primary key fields, but it does show the relationships a lot more cleanly. So this is the one side of the relationship with these two lines, and then this is the many side with this little fan thing. I don't even know what it's called. If anybody knows, shout it out to me or put it in the chat. But and again, so there can be one customer to many events. So that's another way of saying a single customer can organize as many events as they like. Many orders to one customer. That's another way of saying we'd like our customers to place many orders for our restaurant to make money. And you can see here that our join table, one order per dish or per decision orders and one dish per decision orders, which makes a lot of sense considering how we modeled it. But yeah, so this is a little bit more clear and I could get used to this tool. I'm going to show you one more though. And this is my favorite by far because it shows exactly which foreign key fields map to which, from the many side, map to which fields on the one side. This is generated by a free online tool actually called, I thought I had it in my notes. No, I don't remember what it's called, but I'll put it in the slides for sure. But yeah, so you see here that dishes, many dishes, favorite dishes, to one dish. One customer to many events. One customer to many orders. So that's, and it shows the foreign key fields with a direct line to the referenced field. Now, you might notice that these symbols, so it still has the fan symbol that was in the MySQL Workbench ER diagram from the prior slide, but this is a line on the one side and this is a circle on the one side. So what about that? Well, and there's a circle for the favorite dish ID relationship too. So what do you think that means? Anybody have a guess? Yeah, so that means that this is not a required relationship right here. So the circle means 0 or 1 on this side to many on this side. So some customers might not have favorite dishes, which is just fine with us. We're a restaurant proprietor, so we don't care. As long as they like some things on our menu, everything they like is equal. Again, this is a events table has the same type of relationship to customers, except the opposite way. And I don't know if that's a good thing because you might want to require each event to be prepared from the get-go, know the contact person who's organizing, right? So this might point to a design flaw in our schema, which we can then correct. That's why I like this diagram style the most. All right. This is something I pulled offline. And it's supposed to be the official specification for the syntax, but none of the ER diagrams that I have before adhere to it fully. For example, the MySQL, so one and only one is the 2 lines, and I think that makes sense. But with the optional fields, it doesn't, the MySQL workbench version of the ER diagram generator does not indicate optional fields. So 0 or 1 is supposed to be circle with a line, and ER diagram, even my favorite one, does not fully capture that. So I don't know if any ER diagram tools adhere to this 100% or not. I don't know. All right. Any questions before we enter the last section of our topic?
Just curious, like with all of the experience you probably have, like looking at relational databases, is it just a bunch of like ID numbers like throughout your like main sheet? Because if you're indexing all of these things and like relating back to another table, then wouldn't it be just like a lot of just numbers relating back to other tables?
A lot of it is actually, but some of it is actual data, like the customers table contains actual data, right? But the favorite dish ID is, number, right? So you'd have to go look at the dishes table to figure out what dish that dish might be. That's what you're saying?
Mhm.
Yeah, so we're gonna actually figure out how to get that information out into a single report view right now.
Okay, cool.
From query. Any other questions from online? Okay, well, let's get to it then. Let's answer your question. All right, so this is gonna be the workshop. And so the first thing I want to do is try to kind of related to that question you brought up is see customer names, order IDs, and the dishes that were ordered since January 1st, 2025. All right. So we're going to start simply with the leftmost side of this query. We're going to get data from the customers table and then build our relationships from there. So I'm going to switch over to my database view here. I'll take a moment to familiarize you with all the data in here. So we got 25 customers, 3 dishes, and then we have a pre-populated 6 orders. You notice that the foreign key refers to customer number 3 on 2 orders. So she or he ordered twice from a restaurant. The events table we're not even going to worry about for this. And then I pre-populated the dishes and orders table with some foreign keys values. And you'll notice that if you look at the orders, there's 3 dishes in order 1, 2 dishes in order 3, or 2 rather, and et cetera, et cetera. Okay. Now I'm going to flip over to my query tab and then just delete all of that. And then we're going to start by selecting ID, first name, last name from customers. Spell right. Notice that my client tool, ID SQL, highlights things when I type them right. All right, and then this brings up this data. So at the end, this is not anything that I'm looking for except for the customer names. I'm just building my query incrementally. So we got the ID column, the first name and last. Great. All right. Moving back to my slides now. All right. So we're going to create a relationship between the customers and orders table by joining those 2 tables together. So I'm going to, again, the syntax is from customers, join orders, on customers.id equals orders.customers_ID. All right, so again, this is the foreign key in the orders table, and this is the primary key in the customers table. Now, we could have inversed these keys, and it wouldn't have made a difference. They're communicative. But the order that we specify the table's names in does matter for an outer join. Fortunately, we're only using the join keyword here, not left join or right join. And that defaults, most RDMSs default to inner join, because that's the most common thing you want to see is show me all the records on one side of the relationship that have corresponding records on the other. And so let's update our query with this information. So I'm gonna drop down to a new line here for our from clause on customers ID equals orders customers ID. All right, does that look right? Let's play it. Uh-oh, error. Let's read it. Column ID in field list is ambiguous. Does anybody know why? All right. We have an ID column on our orders table and an ID column on our customers table. They're both the same name. So when I ask for the ID column field, the database engine tells me that there's which one. It doesn't know which one I want. So the RDMS is kind of helping me by saying it's ambiguous, which means it doesn't know which order or which ID column I want. So we're gonna have to be a little bit more descriptive in our query. I'm gonna put the customer's table name in front of the field name. And you notice that the concatenator is a dot here. So table dot field. That runs. Now we can also add our fully qualified name in front of each field to make it more clear which table it's coming from. We can also, a fully qualified name would be the schema name dot table name dot field name. And this is particularly useful syntax for when you're doing cross schema joins, which I highly recommend against. I have been burned here in the past. Meaning that you have multiple databases on a single system that you're trying to query across. Now, understand the real world's messy, and you might have some constraints in real life that prevent you from controlling the schemas. But if you do have control over the schemas, one schema. Okay. Let us continue. So I'm gonna add the orders ID to this query. And notice I'm using the fully qualified name. So now the column names are ambiguous though in the output report, right? Who knows which ID is which? We'll get to that. But we already know how to do that, right? Add an alias, order ID. That makes it clear. Yes.
What if you wanted to do rename multiple columns?
Oh, yeah. So we can rename this, add aliases to as many as we want. For example, customer's ID. Now it's even more clear what the data we're seeing is. All right. So to back up, we have joined the customers table and the orders table together on this foreign key relationship to the primary key. So we have this part of the business case covered and this part covered, right? Now we need to add the dishes. So let's refer back to our entity relationship diagram. All right, I'm going to use this one. And notice we have to traverse to get to the dishes table, to the orders table. We have to traverse through the dishes and orders join table. So I need to create a relationship between these two tables to understand what's in this, to get to this data right here. So I'm going to do that right now. So I'm going to create a join, an additional join to the dishes and orders table. All right, let's go back to our query. And notice that also, I meant to point this out earlier. There's a semicolon on the end of our statements, and that is equivalent to the period. So I can omit this client and it'll just assume that the semicolon's there. If you're using the command line or any other interface, you best have that colon or semicolon there rather. So I just by habit, just add it. All right, now we're gonna have to deal with multiple joins. So I'm gonna put the join on its own line. And then I'm gonna add another join. On orders ID equals dishes and autocomplete, nice. Orders ID. So we are joining the orders table in this line 4 to the dishes and orders table. And this is the foreign key that points back to the primary key in the orders table. Now I'm going to have to add some more information to our select clause. So I'm going to put each select on its own line, each select field, and that makes it a little bit more clear. Also going to increase the size of our query window. And let's just see if this runs. Okay, great. It runs, so we don't have any syntax errors in this query. Now we have to add the dishes in. So dishes in orders, dish ID. We'll just do that for now, and let's see. ID. Okay. All right. So we have the dish ID number. That's good, right? But that's not really what we're looking for here. Per the question that was asked earlier, like, what does dish one even mean, right? So I'm gonna say as dish E. Oh wait. Ah. That is referring to the orders and dishes primary key. So we're getting this number from the query instead of this number as it's written down, because I just asked for that field, which gives me back this. That's not what I want. I want this information here. So I'll correct my query. Or, sorry, dish ID, right? Underscore ID. Come on. There we go. All right. That looks better. So any steak ordered in order number 1, whatever dish number 3 is. All right. But where is the dish name stored? Well, it's not in the orders to dishes table. It's in the dishes table. So I'm going to add yet another join from the dishes table, or the dishes and orders table, to the dishes table. On dishes and orders, dish ID is the foreign key equals dishes ID. Like I said, I refer to the primary key on this side of the equal sign and the foreign key on this side of the equal sign, and then I reverse it in this query. So the order of the join fields as it relates to the equal sign operator does not matter. And again, I'm just gonna run this to make sure I got my join syntax correct. See, I don't. Dishes and orders, dish ID, well, it's dishes ID. Run that again. That's good. All right. Now I have connected I had a diagram in the slides. I apparently don't. So I'm just gonna add a new thing, dishes, name. There it is. So now we know that Paige Turner in order number 2 ordered dish ID 1, which happens to be pizza. All right. Everybody understand? Kind of. I know I'm moving fast. I have to cram an entire couple weeks of semesters into a 90-minute workshop. So let's take a break. All right. All right. This is it on so one thing that we've explored in our intro to SQL workshop back in October, which I want to touch on here, is these queries can get quite verbose. So it's useful to use table aliases. So I'm going to just add some table aliases. So I'm going to refer to my customers table as C. And I'm going to replace every instance of it in my query with just C. And make sure that runs. It does. And then I'm going to refer to my orders table. Notice I'm adding these aliases down in the from clause, on the select clause as O. And then again, I'm going to replace every reference to the orders table in my query as with O. And then I'm going to replace the dishes in orders, DIO. And finally, the dishes table with the. Now this is a trade-off because we no longer understand this querying. If we look at just at the select clause, we have to reference the alias name from the from section, but it is a whole lot less verbose. And if we run it, again, make sure it still works. Yeah, it does. This is an option that you have. Notice that the aliases for the tables are separated by a space and then the alias name. And then also they can be multiple letters. Probably the same naming rules as the table names. So you can come up with like an alias that's the exact same name as the table, but that defeats the purpose. So we've polished, well, we haven't polished this yet because we have one more requirement to meet in this report definition, which is we have to get all of the data just from January 21st, 2025 going forward. All right. And so we're going to have to add a where constraint. And what table keeps track of the date that the order was placed? Well, I would assume it's going to be the orders table. And yeah, there's a date time column in the orders table that tells us exactly when that order was placed. So greater than or equals to. So we want to get everything from January 1st, 2025, midnight on. Now, technically, I could have omitted that information from the query and it would just assume that it was 00000. But I like to be as descriptive as possible in my queries so that humans can also understand exactly what data I'm looking for in addition to the computers. And let's see. Ooh, Now we got fewer rows, 7 rows instead of whatever number we had before. I'm just gonna comment this out. So we had 12 before, and when we're only getting this year's orders, we have 7. So it's working. All right, and then that's the next slide. I just had that on the next slide. And we can add Boolean logic to our where clause. So if we want to get 2 conditions instead of 1, orders ID greater than 5. Or 5. ID. I'm referring to the name of the table itself versus the alias now, so I have to use aliases, otherwise it will yell at me. So again, standard Boolean logic works here, just like anything else. You can put precedents in, but that's really out of the scope of the. Let's just make sure our query works with simple date time. Yeah. All right. Any questions about that before we move on to another one? All right, we got 15 minutes, so let's see. Before we move on, though, let's polish this query up a little bit. Customers ID. Our business case didn't ask for the IDs of the customers, and they're arbitrary anyway, so let's take that out. Again, we don't want the dishes ID either. We just need that relationship to join the dishes to the orders. So we'll take out that too. And then run it. And move the orders ID to the start. That's basically what we're looking for primarily. And then add an alias to the dish name. So now the report is a little bit more intuitive. Order ID 3, ordered by crispy bacon, ordered chicken. And as a final polish, we'll add the date time column to the orders. I'll push it right back up against the order ID because those 2 things are related to each other. So this tells us that order 3 was placed on February 18th, 2025 by crispy bacon and ordered chicken. That's all that is required. That we've satisfied our report in this case. Let's move on to another report. I want to see the full bill for order number 2. Well, that requires just a little bit of modification to this query. So we're going to back up. We're still going to keep our relationships the same because we need to know the dish names and the prices now. And that's both stored in the dishes table. We have the name and the price. But we are going to modify our where clause to just show order number 2. So let's just take this date time out. Orders ID equals 2. Oh, heck, I'm still referring to the orders table by its full name. I specified an alias for that table, and that's a no-no. If you specify an alias for a table, you've got to stick to using that alias for the whole query. So OID equals 2. Okay, now we have some information, but we just need to add the price. The price so thank you. I need to read these error messages more. All right, so now we have the price of each dish for order number 2, right? But that's not exactly what this statement was requesting. It asked to see the full bill. So what do we need to use? This is going way back to when I started this presentation by reviewing the October's material. So I'll just tell you, we need to use an aggregate function. So we need to see the full price, which implies that we need to add these two values together, right? So I'm going to just say sum price. Now that sum is a magic keyword. It'll modify the way the database engine queries the data. But we will see the full price, $17.50 for that order. Notice though, it doesn't have any mention of the second line item. So basically what the engine's doing is saying, okay, well, I'm gonna query the dishes in order number 2, but I need to aggregate them somehow. So I'm just gonna barf out the first row of data, even though it's not fully relevant to the query that I want to see. So we don't need any, this column right here on number 6, it's not accurate anymore because it's only one item in the total order. So we're just going to remove it because it creates more confusion than it solves and just show the full order price. So this tells us that in order number 2, which was placed on February 18th, Paige Turner ordered 2 items. Let's see if we can add that. Count the ID. Ordered 2 items. That came to a total of 17. We have 2 aggregate queries here, or clauses, I should say. We're using the count function and the sum function. And like I said, the aggregate functions and all functions really vary from database engine to database engine. So these would be totally different on Postgres or MySQL Server. But I'm just using the MySQL version right now. Like I said, in my October workshop, every database engine implements SQL a little bit different. That's just the sad state of affairs. Okay, 8 more minutes. Let's do one. I want to see the full bill for all orders. So we're not going to use this where clause anymore. We're just going to get rid of it because now we want to see the full bill for all orders. Let's run it. What did the database engine do? Well, right, it summed up every single order in the first row. So all together, our customers have ordered $80 of meals over all time. However, I don't think that's what we wanted to see, right? We want a report that shows each order with the total bill. All right. So this involves a new concept, which is fairly intermediate to advanced. But we want to group by OID. This tells the engine to modify or more information about the query we want. So we want to group by order ID. And lo and behold, we get the full price of every order. Okay. And that is represented on this slide right here. We also use the concat function in this slide. So we're just going to combine these two together. The space in between. And we're going to add some aliases to get rid of those ugly names for the aggregated fields. So customer name as num items and as full or something like that. All right. Now we can print this report out or export it or whatever and give it to whoever asked for it. And confidently. And I think that is where we're going to leave it today. I had one more query to show you, and it related to our discount that we discussed in third normal form. AARP defines senior as 55 or older. That's really offensive to me as a 40-something-year-old. So I'm going to define it as 65 years old instead. And you know that you'll remember that this is not the correct way to calculate that senior price. Yeah, let's just do it. We'll add a where clause. I'm going to do this very quickly though. And I need to remember the syntax. Where timestamp diff year per date greater than. Okay. That weird where clause is kind of saying get everybody over 55 years old. Or, to not offend Casey, 65 years old. Let's see if it runs. Oh, you know what? Delete my group by. Oh, I eliminated a I have to tell it which column to reference and which table to calculate that based on, right? Let's see. I have 0 people over 65. Ooh, okay. Huh. I guess that has to be offensive to me then. There's 2 people over 55. But we have a full price listed, which is not what we want, right? So we're going to have to do a couple other things. This query. Basically divide this full price by 50%. So we'll just add a couple more parentheses here. And then multiply it by 0.5, right? As discount price. That's better. Okay. That is how you manage to solve third normal form values in the database, either by doing it in your query or in your application code that sits in front of the database. We're out of time, folks. So important things that we didn't cover today, there's a list of them. And if you want to continue your database and SQL journey, I actually stole our restaurant example from a LinkedIn Learning video on purpose, because based on what I've covered in this workshop today, this video training series, which is really good, by the way, covers a similar use case in much more detail. And so if you're interested, I think the only difference is that the presenter in that series, prefers camel case names, so like capital letters. I prefer snake case, which is all lowercase letters separated by underscores. But, you know, doesn't really matter. The key is to keep it consistent. Now, if you enjoyed this workshop, please use that QR code to tell us what you think. And it's really important that you fill out the survey, because this helps us develop the curriculum for this workshop. So if you wanted more SQL and less data modeling, let us know, because we will adjust the curriculum based on your feedback. All right, I'm gonna leave the last minute if anybody has any questions. please stay in the chat room online and I'll answer them there. Or come up and see me, the in-person attendees. But thanks a lot for coming today. I really appreciate your attendance. It validates me as a person. I will send out a recording of this workshop along with the slides and all the materials. And if you didn't get a chance to fill out the survey in this hour and a half, I'll send out another request to do so in that email. All right, cheers.
Thank you.
Yeah.